Okay, so as I mentioned in the last podcast, we will look at a new species of phytoplankton found in the ocean by Australian researchers that shows that it's a mixotroph, which means it can photosynthesize but also predate on particles. It's a very unique strategy. This happens on land as well. For example, the Venus flytrap, which is a photosynthesizing plant, can capture insects and get additional nutrients like a multivitamin supplement we take. So in the ocean, it's always a question of not only how much carbon is exported out of the system to the bottom, but also who does it. So earlier work by Tammy Jackson and Tammy Richardson and I think George Jackson had looked at some data from sediment traps and found clusters of small phytoplankton to be actually adding to the export. So they then built a model to look at average velocity in meters per day versus time for various sizes of phytoplankton, and over time the abundance of the small phytoplankton can increase and they can collide and aggregate and form clusters, and the idea was that that way they could get heavier and sink and have basically settling velocities that are similar. So if you look at the 3 micrometer and 10 micrometer versus 30 micrometer, the peak settling velocities can reach even higher values for the smaller phytoplankton because of this aggregation that they modeled. Of course, the larger ones, 100 micrometer, has large settling average velocity throughout this period of simulation from 8 days to 24 days. So this tells you that it's not just the size of the phytoplankton that matters, but the process by which the export happens is important as well. So the new paper that just came out by Larson et al. In Nature Communications found a new species of dinoflagellate. Dinoflagellate is something that has a flagella which it uses for moving around. Remembering that plankton comes from planktos, which means a drifter, so they are just supposed to be drifting with the currents, but many evolve various ways of changing buoyancy to move vertically or flagella to change direction and so on and so forth. So this Protocentrum CF Balticum, as it is called, is found genetically to be different. It's a protist, so it doesn't. It's a eukaryote, so has a cell, has a nuclei in the cell, but it doesn't belong in Animalia, bacteria, or fungi. So it's a unique thing, and using data and genetic techniques they estimate the relative abundance per million counts here at various places. So obviously it's fairly widespread in low latitudes, coastal regions, open oceans, mid latitudes, high latitudes, and so on. And they did some experiments and looked at chemotactic index in the culture filtrate and mucosphere extract, and the particles that they are capturing by creating this mucosphere to capture the particles they want to eat, like a spider building a web to capture insects, for example. And it turns out that the prokaryotic prey were much higher in the mucosphere extract than the eukaryotic prey, and much higher than in the culture filtrate. And when they looked at cumulative mucosphere per cell as time increased on day 1 and day 2, the organic particles and inorganic particles tell you how much particulate organic carbon is being exported. So you can see that over time the cumulative mucosphere per cell increases for prokaryotic and eukaryotic prey here, and also eukaryotic prey, and so various data show that in fact there is significant increase in the cumulative mucosphere over time, with substantial loading of organic particles from both prokaryotic and eukaryotic prey in the trap they are setting up. So as a summary of Plurocentrum CF Balticum behavior, they show that the photosynthesis happens, and then mucosphere production is also happening. So here the prey is captured by using this mucosphere like a spider web, and there is the phagoheterotrophic consumption, which basically means consumption of particles by the dinoflagellate Plurocentrum Balticum, CF Balticum, and the mucosphere is then abandoned, which results in particulate organic carbon export. And then there is the asexual and sexual reproduction by this particular species, which then comes back to the abundance of the photosynthetic pool of Plurocentrum CF Balticum. So pretty amazing that it has dual reproduction strategy, asexual and sexual. So mitosis, meiosis, and just splitting here, and then having photosynthesis as well as heterotrophic acquisition of nutrients. So question of course is how much addition is made in terms of carbon export by this, and I think in the region that they looked at off of Sydney, I think the estimates were 0.7 to 1%. But it is pretty amazing that even after all this time of observing the ocean for centuries at various levels, we can still find new species, and we can see that they have behaviors that we haven't even thought about. So we always say that nature makes the rules and biology finds the loopholes. So here the Plurocentrum CF Balticum is got flagella, so it can move, probably to avoid predation or to find light, or for finding prey by using this mucosphere. So it is able to use the energy to produce a mucosphere to capture prokaryotic and eukaryotic particles to consume, which means the energy balance is such that photosynthesis is probably giving it enough energy to build a mucosphere, and the heterotrophy of consuming things trapped in the mucosphere are more than balancing for the energy spent to produce the mucosphere. Obviously that's energetic constraints are always important, and evolutionary strategies obviously worry about it. So they are spending some energy to build the mucosphere, catch the prey, eat them, and then abandon the mucosphere with some unconsumed organic particles which contribute to the particulate organic carbon export. So obviously an exciting new result that I wanted to include here. Okay, so I will continue to add other new findings here that are of interest for climate change in any aspect in terms of impacts, solutions, contributions to emissions, or sequestration, and so on. Okay.